tied up in a room, dimly lit, only seeing an eerie silhouette in the distance. The figure asks you a question, and if you solve it, it will let you free. If not, you are to spend the day tied up. Here's the question. Suppose that a manufacturing company claims that an average light bulb lasts 300 days. The teacher randomly selects 15 bulbs for testing. The sample bulbs last an average of 290 days, with a standard deviation of 50 days. If that is the case, what is the probability that 15 randomly selected bulbs would have an average of no more than 290 days? The figure hands you a piece of paper, a pen, and a special calculator with some familiarity. Seems like you're in a bit trouble, as you can't give an exact number to this problem, but then you remember your normal and students' distributions.
A normal distribution developed by Johann Friedrich Gauss is a probability distribution developed to calculate the probabilities of continuous random variables, denoted by upper X and upper N, which has two important values, which are mu, which is the mean of the distribution, and lowered sigma, which is the standard deviation of the distribution. We can determine the probabilities of seemingly infinite values. This is depicted using the normal curve, which the area under the curve is equal to 1 or 100%. Although computing for a specific area under the curve requires us to compute using integrals, an easier way to do this is to use z-scores. To compute for a z-score, we have to use the transformation formula. Z-score is equal to the x value minus mu all over sigma, where mu is the mean and sigma is the standard deviation. These z-scores allow the use of a z-table or a special calculator to retrieve the probability within the left, the right, and in between of the curve. However, there are instances where it does not explicitly say that the distribution is normally distributed, such as in sampling distributions. This is all in part of the central limit theorem. There are two components of the central limit theorem which summarizes the concept behind them. First, when a sampling distribution is said to be normally distributed, then normal distribution is to be applied. However, if the sampling distribution is not normally distributed but has a sampling size greater than that of 30, then we can assume that it approximates the sampling distribution.
In cases where the central limit theorem is applied, the transformation formula is modified to accommodate for the possible error that may occur in computation. For a sampling distribution with a finite population, the standard error can be computed using this formula. Z-score is equal to x bar minus mu over the formula of standard error, which is lowercase sigma over the square root of lowercase n, that is multiplied to the square root of uppercase N, which is the population size minus lowercase n, which is the sample size over the population size minus 1. For a sampling distribution with an infinite population, the standard error can be computed using this formula. Z-score is equal to x bar minus mu all over lowercase sigma over the square root of lowercase n. Using this, we can compute for the probabilities with normal distributions. For example, a mother dog of a boxer breed is carrying puppies. Gestation lengths in days of boxers have a random sample of 30 and forms a normally distributed dataset with a mean of 63 days and a standard deviation of 10 days. What is the probability that a random sample size of 30 will have a sample mean less than 60.5 days long? And what is the probability that a random sample size of 30 will have a sample mean greater than 65 days long? Since the gestation length is stated to be normally distributed, we can apply normal distribution to this problem. Also, since this is a sampling distribution, the transformation formula for an infinite population will be used. We are given 63 as the mean, 10 as the standard deviation, and 30 as the sample size. Substituting for the first problem, z is equal to 60.5 minus 63 all over the 10 over the square root of 30 is equal to negative 1.37. That is equivalent to 0.0853 or 8.53% using the z table. Therefore, the probability that random sample size of 30 will have a sample mean less than 60.5 days long is 8.53%. On the other hand, for the other question, z is equal to 65 minus 63 all over 10 over the square root of 30, that is equal to 1.10. Using the z table, it is equivalent to 0.8643 or 86.43%. However, we are tasked to find the probability over 65 days. This probability is below 65 days. Since the probability under the curve is equal to 1, we can subtract 1 by 0.8643 to find the probability, which is equal to 0.1357 or 13.57%. Therefore, the probability that a random sample size of 30 will have a sample mean greater than 65 days long is 13.57%.
We also have another type of distribution called the student's t-distribution, developed by William C. Ligusey, who was often referred to as student. This distribution is often too useful to distributions lacking the population standard deviation. This distribution utilizes something called the degrees of freedom. This determines the size of the curve, and as the degrees of freedom increase, it also approaches the normal distribution. The formula for the degrees of freedom is as follows. df is equal to n minus 1, where df is the degrees of freedom and n is the sample size. It also isn't just one curve, but a family of curves determined by the degrees of freedom. This can be used when instances arise when estimating the mean of a normally distributed population in situations where the sample size is small and the population standard deviation is unknown.
Just like the normal distribution, a special calculator can be used to retrieve the probability from a range of values. However, a unified table cannot be used here since it cannot be summarized that easily. That is why a t-distribution calculator is used here. The transformation formula for this distribution is as follows. T-score is equal to sample mean minus population mean all over sample standard deviation over the square root of sample size n. For example, suppose scores on an IQ test are normally distributed with a population mean of 100. Suppose 20 people are randomly selected and tested. The standard deviation in the sample group is 15. What is the probability that the average test score in the sample group will be at most 110? We can use the transformation formula to find the t-score of the problem. And that is, t-score is equal to 110 minus 100 all over 15 over the square root of 20 equals 2.98. We can also find the degrees of freedom in this situation. And that is equal to df is equal to 20 minus 1 equals 19. Using t-distribution calculator, we get that the probability that the average test score in the sample group will be at most, which means left of the t-curve is 0.9962 or 99.62%.
Now that you have refreshed your knowledge on normal and student's t-distributions, let's solve the problem of the Erie figure. Recalling the problem, suppose that a manufacturing company claims that an average light bulb lasts 300 days. The teacher randomly selects 15 bulbs for testing. The sample bulbs last an average of 290 days, with a standard deviation of 50 days. If that is the case, what is the probability that 15 randomly selected bulbs would have an average life of no more than 290 days? Solve this problem on your own and we will give the solution. We know that the population standard deviation is unknown, and the sample size is relatively small. This means we can use the t-distribution for this problem. The t-score is computed as follows. T is equals to 290 minus 300 all over 50 over square root of 15, and it is equals to negative 0.77. The degrees of freedom can be computed as df is equals to 15 minus 1, and it is equals to 14. Using the t-distribution calculator the figure gave you, we get that the answer to this problem is 0.2270 or 22.70%. This means that there is a 22.70% chance that a light bulb would have an average life of no more than 290 days. You give this answer and the figure properly screws on the dimly lit light bulb to reveal your math teacher, pranking you for sleeping in his class.